Okay, so this was your main proof in year 13, proving that root 3 is irrational by contradiction. Now, in the example they give you in the textbook, they prove that root 2 is irrational by contradiction, and they tell you that if a squared is divisible by that number, then a is divisible by that number, and that you can assume it. But if they don't tell you that, you have to assume it. So we're dealing with root 3. So we consider if a squared is divisible by 3, then so is a. If we were showing that root 5 was irrational, we would consider a squared divisible by 5. Right, so an irrational number is a number that cannot be written in the form of a fraction. So we would define that as p over q. So what we're going to do, because an irrational number can't be written in the form of p over q, where p and q are integers, and q is non-zero, what we're going to do for the contradiction is assume that it does equal that. That's the contradiction. So you are assuming it's rational, and you're going to prove that this is not true. Okay, where p and q are integers with no common factors. Right, so square both sides. That means that when you multiply both sides by q squared, you'll get 3q squared equals p squared. This means that p squared is divisible by 3, because p and q have no integers with a common factor. That means if p squared is divisible by 3, because of your assumption, p must also be divisible by 3. So I can write p as 3 times anything where that k is an integer. So replacing that back in to the 3q squared is p squared, I'm going to get 3q squared is 3k all squared. 3k all squared is, of course, 9k squared. So I'm now dividing both sides by 3, getting q squared equals 3k squared. This means q squared is divisible by 3, and we know that we can assume that implies that q is divisible by 3. This means that both p and q are divisible by 3. They have a common factor of 3. Therefore, there is a contradiction. Root 3 cannot be written as p over q. Therefore, root 3 is irrational.